Welcome back to the Deep Dive, the place where we take the densest, most complex stacks of sources, from physical chemistry papers to historical scientific notes, and extract the essential knowledge just for you, the dedicated learner.
Today, we're really undertaking a fundamental mission. We're moving beyond just observing what happens in the universe, and we're diving straight into the ultimate question: why does change happen at all?
Exactly. And our subject is thermodynamics, specifically this core conflict that dictates, every chemical reaction, every phase transition, and really the ultimate limits of what's even physically possible.
That's it. We're dissecting the central competition. Think of it as the cosmic balance sheet of change.
I like that. A cosmic balance sheet. We're going deep into the heart of free energy, this powerful engine of spontaneity, and we're going to follow the math all the way down to its theoretical boundary, absolute zero.
And our focus is really twofold. First, just understanding the mechanics of free energy and this incredibly powerful predictive tool, the Gibbs-Helmholtz equation. And second, we'll see how this whole framework forces us to confront the deepest limitations of physical law, especially through the third law of thermodynamics. We're connecting, easily measurable heat to the theoretical limits of order and chaos.
We have a rich set of sources here, and they detail the elegance of this mathematical bridge and the just profound physical consequences of chasing absolute cold. We're going to connect the dots step by step.
And by the end of this deep dive, you'll have a really clear understanding of why certain energetic outcomes are inevitable, why others are impossible, and maybe most fascinatingly, why the universe can never actually achieve perfect stillness.
Okay, let's unpack this. The fundamental tug-of-war between organization and dispersal.
Let's do it.
So we have to start with the core concept that governs all this spontaneity. Free energy, which we label with an F. And our sources, they present this foundational definition of Helmholtz free energy for systems at a constant volume and temperature, right? F equals U minus T times S.
That equation, F equals U minus TS. It looks so simple, but it really encapsulates the entire energetic life of a system.
So what exactly is that F? What is free energy?
When we talk about F, we're talking about the part of a system's total internal energy, that's the U, that is theoretically available to do useful work.
Useful work like pushing a piston, driving a current.
Exactly. Or facilitating a chemical process. It's the available budget for directed action, assuming the system stays at a constant volume and temperature.
And the universal driver here is, well, minimization. I've heard it said nature is inherently lazy.
That's a great way to put it.
Yeah.
Every spontaneous process, every single shift in state, is driven towards reducing the system's free energy. If a process can result in a lower F, it is energetically favored. It'll just happen. Spontaneously. And when F finally reaches its minimum value, the system's hit equilibrium. No more spontaneous change is possible.
But the real challenge is how F is calculated. It's the result of these two massive opposing forces. Our sources call the two terms on the right side of the equation U and TS, the two giants competing for dominance. I think that's a perfect analogy. So on one side, we have U, the internal energy, that's giant number one.
And U represents this tendency toward energy minimization. Think of this as the drive toward order and stability. Systems inherently want to shed energy to get into the most efficient, lowest energy setup possible.
Like everything trying to fall down to the basement level.
Exactly. It's why a tightly wound spring relaxes. It's why highly reactive chemicals release huge amounts of heat in exothermic reactions. They're forming stable, low-energy chemical bonds.
And even something like water freezing into a neat, low-energy crystal, that's also driven by minimizing U.
Yes. This giant is all about organization and efficiency.
Okay, so that's one giant. What about the second one?
The second giant is entropy. Guess. This is the famously slippery measure of disorder, randomness, or, maybe more accurately, the number of ways that energy and particles can be distributed in a system. It drives dispersal and chaos.
Right. But let's look at that equation again. F equals U minus TS. Entropy, S, it has a negative sign in front of it.
Yeah.
And that seems absolutely critical.
It flips the entire script. It's everything.
Yeah.
While minimizing U, the internal energy, pushes the system toward order. Maximizing S, or disorder, also minimizes the free energy F.
Because of that negative sign.
Because of that negative sign. The bigger S gets, the smaller F gets. So this second giant is constantly driving the system toward maximum chaos and dispersal. If a system can find a state with more disorder, it'll move there spontaneously because that lowers F.
Wait, okay. Isn't that a bit of a paradox? We're saying the natural drive is toward chaos to lower free energy, but free energy is supposed to be about useful work. How does a drive for maximum chaos generate something useful?
That's an excellent and a very necessary clarification. We have to distinguish between spontaneity and utility in the human sense.
Okay.
The spontaneous minimization of F just means the process can happen without us pushing it. And often, these highly entropic processes, like a gas expanded really fast, they do produce work, like pushing a piston.
I see.
But the primary drive is just to find the state with the lowest F. The minimization of F is a universal statement. The combination of low energy and high disorder is the most stable place for any system to be.
So it's this perpetual cosmological tug of war, the desire for low energy, U, versus the push for maximum dispersal, S.
And the outcome of this whole competition is decided by one thing: the temperature, T.
Ah, the referee.
The referee, or maybe more like the economic factor that decides the relative cost of energy versus entropy. Temperature is what multiplies S, so it determines how much weight that whole entropic term, TS, carries relative to the internal energy, U.
So let's look at the extremes. What about deep cold, a very low temperature T?
When T gets close to zero, that factor multiplying S is minuscule. The entire TS term becomes nearly negligible.
And in that frigid scenario, the internal energy drive, the U, it wins.
It wins, hands down. Low-temperature environments are fundamentally dominated by the energetic drive. The system favors the most ordered, low-energy setups. That's why matter forms solid, rigid, ordered crystal structures when it's cold. The energy drive dictates organization.
But then if we flip that and dial the temperature way, way up, say, inside a star or industrial furnace.
Now that T term becomes massive, the TS product just quickly overwhelms the internal energy U.
So entropy wins.
Entropy wins handily. High temperature provides the thermal energy to overcome those stabilizing forces of U. Matter just stops caring about efficient, low-energy structures. Solids melt, liquids vaporize, molecules break apart. Dispersal and disorder take over completely.
Which is why steam is favored over liquid water at 101 Celsius, even though steam has way more internal energy.
Exactly. The huge entropic benefit overcomes that energetic cost.
So free energy F is the ultimate balance sheet of this eternal struggle, and temperature is the single variable that sets the rules, tilting the scales dramatically toward organization or chaos.
Now that we've got the ideal sort of on-paper equation for free energy, we have to acknowledge a fundamental truth about reality.
Which is?
Nothing in the real world is ever perfectly efficient.
Okay, so this is where we have to revisit the second law of thermodynamics, but now through this lens of usable energy, F.
Precisely. The second law tells us that for any real process, any actual irreversible change that happens, the total entropy of the universe has to increase. There's always a cost, and it's paid in the currency of disorder. You can't break even.
And mathematically, that means the entropy produced by the system, that T times ds term, is always greater than the heat you actually supplied, delta Q?
Yes, because some extra entropy is always generated just by the process being non-ideal, being real. And this has a direct, profound consequence for the change in free energy, dF.
So what does that consequence look like? What's the inequality?
The change in free energy, dF, is always less than or equal to the work performed on the system, delta W. Or, to put it the other way, the work you get out of a system is always less than or equal to the decrease in its free energy.
And that equal to part, that's the ideal case, right? The one we calculate on paper,
Yeah.
the theoretical maximum.
That's the perfectly reversible case, which is a conceptual construct. It's a process where every tiny step could be reversed without any change to the universe, but in the real irreversible process.
Which is always, every time.
Always in real life. Every time you open a door or start a car. In those cases, the work you get out is strictly less than the theoretical maximum from dF.
So the practical meaning here is that in any real process, we either have to put more work into the system than the minimum required, or we get less useful work out than we calculated.
Exactly. And the difference between that theoretical maximum work and the actual work we get is often called lost work.
It's not really lost, though, is it? It doesn't just vanish.
No, not at all. It's just fundamentally unavailable for directed action. It has been used up in the production of entropy.
It sounds like an inescapable thermodynamic tax.
It is the inescapable tax levied by chaos. That lost work increases the disorder of the system and its surroundings, satisfying the second law, but it makes that energy unavailable for, say, mechanical or electrical action. It's why no engine can ever be 100% efficient.
Okay. So we've established the conceptual struggle and the practical cost. Now let's dive into the mathematics that allows scientists to actually keep score and make these rigorous predictions.
Yes. So if F equals U minus TS defines the components, the Gibbs-Helmholtz equation is the powerful engine that connects them all in a predictive way.
And to really get the utility of this, we need to take a quick formal look at how physics uses calculus to establish these relationships. This is where the mathematical bridge is built.
Right. We start with internal energy, U, and U is defined as a state function. This is important. It means U only depends on the current state of the system. It's temperature, volume, so on, not the path you took to get there.
Right, so it doesn't matter how you got there, just where you are now. And if U is a state function, we can define it based on its natural variables, which are volume V and entropy S.
Correct. And mathematically, if U is a function of V and S, then the total change, du, is a sum of its partial derivatives. A partial derivative just tells us how U changes when you tweak one variable while holding the other one constant.
Okay, so we have this purely mathematical expression for du, and then we compare it to the physical statement from the first law of thermodynamics.
We do. The first law gives us du equals negative pressure times dV plus temperature times ds.
And by comparing the coefficients, the terms in front of dV and ds,
We establish these fundamental physical relationships. The one that's critical for our journey here is the one for ds. The coefficient in front of ds is T, temperature.
so temperature, T, is mathematically defined as the derivative of the internal energy, U, with respect to the entropy S, while holding volume constant.
And that's profound. Temperature, which we measure with a simple thermometer, is actually defined microscopically by how responsive the internal energy is to a small change in disorder. We've just mathematically quantified the connection between energy and chaos.
Wow. Okay, so now we pivot. We move from internal energy to free energy, F.
Yes, and F is often more practical in the lab because it depends on temperature T and volume V variables we can easily control and measure.
So we go back to the definition, F equals U minus TS. And to find the total change, dF, we differentiate the whole thing.
And we have to use the product rule on that TS term because both T and S can change. So that gives us dF equals du minus TdS minus SdT.
Okay.
Now comes the really elegant step, the magical cancellation, as our sources call it. We substitute that first law definition of du that we just confirmed, that du is dash b dv plus TdS, back into our dF equation.
Let's see it happen. We plug the du expression in, and suddenly we have a positive TdS term from the first law and a negative TdS term from our differentiation.
They just annihilate each other. They cancel out completely.
Wait, so they just disappear?
They do. And the terms related to the messy, heat-dependent change in entropy just vanish, leaving us with an equation that depends only on pressure and temperature changes, which are much easier to control.
And what's left is the total differential of free energy. dF equals negative p dV minus S dt.
That's it. And that resulting differential is the central pillar of the Gibbs-Helmholtz framework. So we repeat our trick. We compare the coefficients again.
And we can see it clearly. The coefficient in front of dt is negative S.
Which gives us our new key relationship. Entropy S is the negative partial derivative of free energy F, with respect to temperature, holding volume constant.
This is a massive aha moment, isn't it? We've taken entropy, this abstract idea of disorder, and we've mathematically defined it in terms of how sensitive a system's available energy is to a change in temperature.
It's a huge conceptual leap. The definition of entropy is transformed. It's no longer tied to path-dependent heat transfer like the old Clausius definition. Now it's defined solely as a property of the system's state, based on its temperature dependence. This allows us to connect the abstract with the measurable.
So the final step is to close the loop and create the famous Gibbs-Helmholtz equation itself.
Right, we take that new derivative definition of S.
What we just found.
And we substitute it back into our original starting point. F equals U minus TS.
And we just found that S equals the negative derivative of F with respect to T. So when we plug that in, the two negative signs cancel out.
And we get the result. F is equal to U plus T times the partial derivative of F with respect to T.
And that is the Gibbs-Helmholtz equation.
That's it. And it's arguably one of the most important equations in all of physical chemistry.
So why? What makes this equation such a big deal for, the chemist, the engineer, the biologist listening right now?
Its significance is just. It's profound because it creates this incredibly powerful predictive bridge. Imagine a chemist wants to know if a reaction will run spontaneously at, say, 500 Kelvin and how much work it can do. They need to know F.
Right.
Before this equation, they'd have to measure S and U separately, which is complicated. But now, if we know the internal energy, U, which we can measure relatively easily with calorimetry experiments, we have a differential equation we can solve to calculate the theoretical free energy, F, at any temperature.
It connects easy-to-measure thermal properties to the complex energetic potential of the system.
It's like a predictive time machine for chemical systems. It's a game changer.
Okay, so that's the theory. But in practical thermodynamics, you're not usually calculating the absolute F for an entire system, are you?
No, almost never. Whether you're designing a chemical plant or engineering a battery, you really care about the change in free energy between two states.
Between reactants and products.
Exactly. You care about the difference, the delta F, because that's what tells you if the reaction is going to run and be useful.
So you just translate the whole equation into differences.
Right. So it becomes delta F equals delta U plus T times the derivative of delta F with respect to T. That's the form you see in every textbook and industrial calculation. It's the workhorse.
And this lets scientists predict if a reaction will run spontaneously. Delta F has to be negative.
And second, it lets them calculate the maximum amount of useful work the reaction can perform. In battery science, for example, chemists measure the heat released, the delta U, and then use Gibbs-Helmholtz to predict the maximum voltage, which is related to delta F, that the battery can produce at different operating temperatures.
It saves billions in just endless trial and error experiments.
It absolutely does.
There's a catch, isn't there? You mentioned it's a differential equation.
There's always a catch. To solve any differential equation, you need a fixed starting point, a boundary condition. It's called the integration constant.
We need a definitive reference point for F at some temperature, probably somewhere near absolute zero.
Exactly. Without knowing the precise value of F at a specific fixed point, the differential equation just gives you an infinitely large family of possible solutions. It's useless for calculating absolute potential.
And this was the major hurdle facing thermodynamics at the turn of the 20th century. How do you anchor this massive predictive equation?
This is where Walther Nernst, the great German physical chemist, comes into the story. Around 1906, he starts this meticulous research, studying reactions as he pushes experimental temperatures lower and lower and lower. He's the investigator trying to find that missing constant.
And what did he find? What was the physical observation that let him solve a purely mathematical problem?
It was about consistency. Nernst asserted that as the temperature approaches absolute zero, as T goes to zero, the change in free energy, delta F, becomes independent of temperature. It just stops reacting to temperature fluctuations.
So if you were to graph delta F against temperature, T, what does that curve look like as you get really close to 0 Kelvin?
The curve runs perfectly flat. It goes horizontally right into the 0 point. It approaches 0 Kelvin with a slope of 0.
And a flat line means the slope is 0, and the slope of that curve is, by definition, the derivative of delta F with respect to T.
Exactly. Nernst's theorem dictated that the derivative of delta F with respect to T must approach 0 as T approaches 0. And that provided the necessary mathematical boundary condition, the fixed point, that allows the Gibbs-Helmholtz equation to be solved uniquely.
So this simple but profound observation became the third law of thermodynamics.
Or Nernst's heat theorem, yes.
So Nernst solves the calculation problem, but in doing so, he establishes a new fundamental law of nature. So let's explore the really mind-bending physical consequences of this law. If that derivative is 0 at T equals 0, what does that mean for entropy?
Well, we just have to revisit the connection we derived earlier back in section 3. We established that the derivative of F with respect to T is equal to negative entropy, or negative delta S for changes.
So if Nernst is right, and the derivative of delta F goes to 0 as T goes to 0,
then the consequence for entropy is immediate and mandatory.
the change in entropy must also go to 0.
The change in entropy, delta S, must also approach 0 as the temperature approaches absolute 0. And this is a critical realization. It means that at T equals 0, any hypothetical reaction would have to be isoentropic. The change in disorder during that reaction would vanish.
So the system and its products would have to approach the exact same state of minimum disorder.
Exactly. It eliminates any possibility of a reaction being spontaneously favored just because of a massive increase in entropy at absolute 0. That can't happen.
The third law has another powerful observable consequence, right? something about heat capacities.
Yes, it necessitates that heat capacities must also approach zero as temperature approaches absolute zero.
And why does that follow? Why does that make sense?
Well, heat capacity is fundamentally the measure of how much heat energy a body can absorb to raise its temperature by 1 degree. When a body is hot, its atoms are vibrating, rotating, translating. They have lots of available degrees of freedom to store that energy.
So it has a high heat capacity, it can soak up a lot of energy.
Right. But as the system gets close to T equals zero, those degrees of freedom literally freeze out. The atoms get locked into their lowest possible energy states. Their movements become governed by quantum mechanics, and for a molecule to store heat, it has to jump to a higher, quantized energy level.
And at near zero temperatures, the thermal energy available is so tiny that it's just not enough to make those quantized jumps.
Precisely. The system simply cannot absorb the heat, and since it can't store or absorb thermal energy, its capacity to absorb heat is zero. And we see this in the lab. It's a direct physical result of the third law enforcing minimum energy and maximum order.
Okay, so Nernst established that the change in entropy approaches zero. But Max Planck took this a step further, didn't he? He provided the ultimate fixed point.
He did. Planck refined Nernst's theorem into the modern statement of the third law. He asserted that for a perfectly ordered, pure crystalline substance, the absolute entropy S is zero at the absolute 0 point.
So not just the change, but the value itself.
The absolute value. And this did two massive things. First, it provided that definitive, non-arbitrary integration constant we needed to solve Gibbs-Helmholtz for absolute free energy. And second, it elevated thermodynamics. It was no longer just a science of differences, of delta S. It became a science capable of determining the absolute entropy of any substance at any temperature.
Which is incredible. Okay, here's where it gets really interesting for me, connecting these big macroscopic laws to the microscopic world of atoms. We've established that classically, S has to be zero at T equals zero. But why? Why must this be true from a particle's point of view?
For that, we turn to the microscopic definition of entropy from Ludwig Boltzmann. S equals Kb times the natural log of omega.
S equals KBlNA, and omega A is the number of possible microstates, the number of ways the particles can be arranged to give you the same overall picture.
Right, so a messy room has a huge omega. There are countless ways to scatter things around and still have it look like a messy room.
High omega, high entropy. Got it.
So now, consider the state at absolute zero, T equals zero. The system is perfectly ordered. It's a perfect crystal. Every single atom or molecule has settled into its lowest possible energy state. There is no residual motion, no vibration, no swapping of positions.
So if there's no residual motion, how many ways are there to realize that perfect state?
There's exactly one single possibility.
Just one.
The atoms have to be in one specific, perfectly ordered configuration. Therefore, omega is precisely 1.
And since the natural logarithm of 1 is 0,
The entire term, S equals KEALN, collapses to S equals 0. It's this beautiful microscopic confirmation of Planck's law. Perfect order equals 0 entropy.
which leads us to maybe the most famous consequence of the third law, the absolute 0 point cannot be reached.
It cannot be reached in a finite number of steps. And this isn't an engineering problem or a budget problem. It's a fundamental thermodynamic barrier.
Why? What's the barrier?
The barrier is inherent in the entropy change. Any process we use to cool an object has to involve a decrease in that object's entropy. But according to Nernst, as we get closer and closer to T equals 0, the change in entropy for any process also approaches 0.
So the closer we get to 0, the less effective our cooling process becomes. We get diminishing returns.
Vanishingly small returns. To remove that last little bit of residual entropy and actually hit T equals 0, you would need an infinite number of steps, each one giving you an infinitesimally smaller reduction in temperature. We can get spectacularly close. We're talking billions of a Kelvin now. But absolute 0 remains forever a conceptual limit, not an achievable physical reality.
The system always retains a tiny residual shiver.
It does.
Okay, to bring this whole journey full circle, let's just clarify one last point about entropy. Historically, the definition was a bit of a mess until the third law came along and fixed things.
It was. We essentially had two ways of looking at entropy. The classical Clausius definition, which is great for process changes, delta S equals delta Q rev over T.
But as we said, that only gives you differences. Delta S, it can't give you an absolute 0 point.
Right. And then there was this statistical definition from Boltzmann's ideas. And early concepts sometimes phrased it as S being proportional to the logarithm of the probability, P, of finding the system in a certain state.
And our sources point out a pretty serious mathematical flaw with using probability P in this context.
It's a simple one.
Right.
Probability P has to be a number between 0 and 1. And if you take the natural log of any number that's less than 1, you get a negative number.
Which would mean that the entropy of pretty much every system in the universe would have to be negative. That's absurd.
It is. It fundamentally contradicts the physical reality that Planck solidified with the third law, which says S equals 0 is the absolute minimum possible entropy. It can't be negative.
So the fix wasn't to throw out the statistical approach, but just to refine what's inside the logarithm.
Exactly. The resolution was moving away from probability P to the number of microstates, omega. The correct definition is S equals KB ln A, where omega is the number of possible microstates.
And unlike probability, the number of microstates, omega, is always a number greater than or equal to 1.
Which ensures perfect consistency. We check the boundary condition again. At absolute 0 perfect order, omega is 1. The logarithm of 1 is 0, so S equals 0. The third law provided that necessary fixed point, and it forced statistical mechanics to adopt this rigorous definition, ensuring that, well, everything aligned perfectly.
What an incredible journey. We started with this universal competition between energy and entropy, the engine that dictates all physical processes, and we followed the math all the way down to the ultimate unreachable stillness of absolute 0.
We've seen that the minimization of free energy, F, is the universal motivator for change, and we derive the incredibly powerful Gibbs-Helmholtz equation.
That predictive bridge that lets scientists connect the easily measurable reality of heat changes to the ultimate energetic potential of a system. It really did transform chemistry.
It did. And finally, we explored the third law, born from Nernst's search for an integration constant, solidified by Planck's assertion of 0 entropy, and then beautifully justified by Boltzmann's microscopic count of states. It establishes the speed limit of absolute cold.
Understanding this gives you, the listener, not just technical knowledge, but a profound appreciation for these invisible, structured laws that govern every energetic transaction in the cosmos.
And here's a final thought. If the universe demands that perfect order, S equals 0, is physically unattainable, that reaching it would require infinite resources and infinite time, what does that imply about the necessary persistence of tiny residual disorder and complexity in every single system, even in the coldest vacuum of space? It seems that a degree of chaos isn't just common, it's a necessary foundational state of existence.
Food for thought until our next deep dive. Thanks for learning with us.